Today we discuss on important topics related to series of non-negative terms. Okay, we start series. Okay, series of non-negative terms. We also discuss one theorem first. This one is known theorem. We start if 0 less than equal to alpha less than 1, then summation n equal to 0 to infinite alpha to the power n equal to 1 divided by 1 difference alpha. Okay, if alpha greater than 1 or greater equal to 1, then summation n equal to 0 to infinite n to infinite alpha to the power n. Okay, diverges. We now prove this theorem first. So what we do, we also known about from geometric series, this one Sn equal to summation k equal to 0 to n. Okay, alpha to the power k equal to here 1 minus alpha to the power n divided by 1 minus alpha. Okay, sorry, alpha to the power n plus 1. Okay, also do it in some solution process. Then this one is factored 1 minus alpha multiplied by 1 plus alpha squared dot dot dot. Okay, alpha to the power n. Then this one happen. So also put here n tending to infinite, then this one become k equal to 0 to infinite alpha to the power k, and this one become limit n tending to infinity as n equal to what? Here limit n tending to infinite 1 minus alpha to the power n plus 1 by 1 minus alpha, and alpha here belonging to 0 less than equal to alpha less than 1. So alpha to the power n plus 1 tends to 0. Okay, as n tends to infinite, then this limit equal to what? This limit equal to, we obtain here 1 by 1 minus alpha. Okay, not a problem at all. Now we're going to discuss another portion. We also put here, put alpha equal to 1, then what happened? Then n equal to 0 to infinite alpha to the power n equal to 1 plus 1 plus 1 plus dot dot dot, and tends to plus infinite. Okay, so not a problem at all. This is divergent if alpha greater than equal to 1, and this one is convergent if alpha less than 1. Okay, so we now further proceed. We erase that portion and going to further discussion of that one important theorem related to this series of non-negative terms. Okay, here we write this statement theorem. Suppose a1 greater than equal to a2 greater than equal to a3 dot 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 greater equal to 0. Okay, then the series here summation n equal to 1 to infinite a to the n converges if and only if the series summation k equal to 0 to infinite 2 to the power k a to the power k, okay, equal to, in this way, here a1 to a2 dot 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 4a4 8 8 converges. Okay, we use here another theorem, that means we prove this theorem. Just an converges if and only if this series converges. Okay, so we proved and we used one important theorem in here. We write statement of this theorem: a series of non-negative terms, okay, converges if and only if its partial sum form a bounded sequence. Okay, so we using this theorem also first write partial sum. Sn equal to what? Sn equal to here a1 plus a2 plus dot an. Okay, and here we write tk equal to a1 plus 2a2 plus here dot 2 to the power k a to the power k. Okay, then what happened? Then we age our portion and going to further discussion of that. Then for n less than 2 to the power k, here we write Sn less than a1 plus a2 plus a3. Okay, here a4 plus dot a7. Okay, and in this way we write a2 to the power k dot plus dot a2 to the power k plus 1 difference 1. Okay, if n less than 2 to the power k. Okay, then what we obtain? We obtain this one less than equal to. Okay, and we obtain in this way less than equal to a1 here 2a2 plus here 4a4 plus dot here 2 to the power k a to the power a2 to the power k. Okay, then this one equal to tk. Now another way, if n greater than equal to 2 to the power k. Okay, then what happen? We erase lower portion also. Now I'm going to further discussion of that. Here Sn equal to a1 plus a2 plus a3 plus a4 dot here a2 to the power k minus 1 plus 1 dot a2 to the power k. Okay, if n greater than equal to 2 to the power k, then Sn greater than equal to. Okay, not a problem at all. Then what happened? We write in this way, this one greater than half a1, okay, plus a2 plus 2a4 plus dot 2k minus 1 a 2k. Okay, we also use here one, then first we also see that in statement of the theorem given that a1 are decreasing sequence. Okay, if an are decreasing sequence, that means a1 greater equal to a2 greater equal to a3. So here we put this one, and we also use this one. Okay, then this one we write here equal to half tk. Okay, then what we get? We get 2Sn greater than tk. Then what do we obtain? Here we obtain Sn less than equal to tk. Here we obtain 2Sn greater than tk. Okay, then what happened? Then Sn and Tn are either both bounded or unbounded. Okay, or both unbounded. Okay, then what happened? Then obviously if tk bounded, then Sn bounded, and so we use this theorem. That means boundedness of partial sum. That means partial sum from a bounded sequence, then this is convergent. Okay, that means if a n converges, then summation 2k a2 to the power k converges. And also convert, if this one converges, then an converges. So we prove this theorem also. Okay, I think not a problem at all. Now we also use this theorem. We're going to another theorem related to that topics. Okay, we erase that our portion and going to discuss another familiar theorem. Okay, so we write statement of this theorem here. Summation 1 by n to the power p converges if p greater than 1. Okay, and diverges if p less than equal to 1. So we also prove that theorem now. We use that portion and going to further discussion of that. Here, if p greater than 0, okay, then what happened? Then we also see that then summation 2 to the power k a 2 to the power k, okay, k equal to 0 to infinite, equal to what? Equal to summation k equal to 0 to infinite 2 to the power k, here 1 by 2 to the power k whole to the power p. Okay, then what happened? Then this one k equal to 0 to infinite 2 to the power k 1 minus p. Okay, then here 2 to the power 1 minus p. This one, that means if less than 2 to the power 1 minus p less than 1. Okay, if and only if 1 minus p less than 0, that is here 1 less than p. Okay, that means this series convergent for 1 less than p or p greater than 1. Okay, so we use this this series we also call summation 1 by n to the power p converges for p greater than 1. Okay. Now, now we also write if p less than 1, then less than equal to 1, then this one is divergent. Okay. Now we going to another topics that is related to that theorem. We also write here theorem. We write theorem if p greater than 1, then summation n equal to 2 to infinite 1 by n log n whole to the power p converges. Okay. And if p less than equal to 1, then the series diverges. Here is our portion, and using this theorem we also prove that. Okay. Now the monotonicity of logarithm function, okay, implies that log n increases. Okay. So n log n also increasing sequence. Now what happened here? Also write 2 to the power k 1 by 2 to the power k log 2 to the power k whole to the power p. Okay. That means here n log n whole to the power p, here 2 to the power k log 2 to the power k whole to the power p. Okay. So this one equal to, we solve summation here 1 by k log 2 whole to the power p equal to summation 1 by k to the power p log 2 whole to the power p. Okay. And similar way also see that this one converges. That means if k to the log 2 whole to the power p common, then 1 by k to the power p, then this one converges for p greater than 1. Okay. That means this one converges for p greater than 1. Then what happened? Then we see that this one summation n equal to 2 to infinite 1 by n log n whole to the power p also converges for p greater than 1. Okay. That means using this theorem we also prove this one also. Okay. Now we also see another one. Okay. That means we also see this theorem. Now we another one develop also. Okay. Using this theorem. Here n equal to 3 to infinite 1 by n log n. Okay. Log of log n whole to the power whole square. Okay. this one converges or diverges. We also handle this one. Now we know about that same procedure, that means log of log n also increases, also this one also increasing sequence. So here n log n, log of log n also increasing one. Okay, now we write in this way. That means we also write summation 2 to the power k 1 by a 2 to the power k, means here 2 to the power k log 2 to the power k, here log of log 2 to the power k square. Okay, equal to what? Equal to, we also 2 to the power k cancel, then this one 1 by k log 2, here log of k log 2. Okay, this one square. Then what happened? Then in this way also obtain, that means k log 2, here log of k plus log of log 2 whole square. Okay, then what happened? Just we then think about that. This one k log k square. Okay, just this one some constant adding, and this one are constant multiplied. Okay, not a problem at all. So this one here we also write in this way summation 1 by log 2 k, and here log k plus something with log of log 2 square. This one converges for p greater than 1. We are using this theorem. Okay, and that one proof we using summation 1 by n to the power p converges for p greater than 1, and now we use also see this theorem, and this one converges for, that means for help of that series. Okay, so we write about that. Summation n equal to 3 to infinite 1 by n log n, log of log n square converges for p greater than 1. Okay, so today we stop here. I think if you get this type of video, please subscribe my channel, follow my channel, see this video regularly, click on like option, and obviously subscribe my channel. And today I stop here. Thank you. Okay.